Okay, welcome class for this course, electromagnetism. So we are now on our last topic or chapter sa kaninga course. This is on special techniques. So after learning those things nga sa atong previous discussion on finding the electric field using the Coulomb's law, we can also find the electric field using the Gauss's law, and also knowing those equations related to it in finding the charge density given the potential or the other way around. So next is we will now move on to some techniques na mga useful siya sa electromagnetism in finding electric field, also the charge density, wherein maglisod na o gamit ang katong mga techniques katong nabawaan sa previous because it might not be applicable, but with these new techniques, we call it the special techniques, we may be able to find solutions to some problems wherein difficult siya at first, but actually nara siya way out. Okay? So we will focus on these special techniques, specifically on the Laplace equation. So we are all familiar with the Laplace equation already since time and time again, mugawas gini siya nga equation minsan asa. And permanente ni siya na agyud the whole chapter sa kaninga course, electromagnetism on special techniques, will be dealing with the Laplace equation, but on Laplace equation in one dimension, in two dimension, and also in three dimensions. Okay. So we recall this Coulomb's law. Wala ang equation, right? We are kanisha familiar na kita ani nga form. So the primary task of electrostatics is actually to find the electric field mo gina siya given a stationary charge distribution. That's why it's stationary, so static siya. So given this distribution rho, we can find the electric field in this form. So kani ang gamit in equation 1. But unfortunately, integrals of this type in equation 1 can be very difficult to calculate for any but the simplest charge configuration lang yun. And occasionally, we can get around with this equation by exploiting the symmetry. Let's say na asymmetry ba ang imong system, so that's why we can use the Gauss's law. But ordinarily, the best strategy is to first calculate the potential V. What I mentioned, di ba, itong previous topic. So it's a lot easier to make a detour because dealing with potential, which is a scalar quantity, is a lot easier than dealing with this vector quantity electric field directly using equation 1. So somehow mas tractable ni siya if we calculate first the potential given this equation 2. So scalar naman siya, you just do the integral. Okay, then you can get the potential given the charge distribution, may it be volume, surface area, or a line charge distribution. But still, this equation 2, medyo lisod gihapon ni siya, often too tough to handle analytically. So moreover, in problems involving conductors, let's say involving conductors, rho itself may not be known in advance. So unsa kay buhaton nato if dili siya known in advance, right? Ato lang let's say ang given, ang naara gyud nga given is uncharged lang, say total charge, not the rho. So we need to approach this type of problem differently. So lahi na pud nga technique atong gamiton. So in such cases, okay, it is fruitful to recast the problem in differential form using the Poisson's equation. So this is the Poisson's equation. This is the familiar equation na sa tua as physicists. So kani siya del square naman siya of this potential equals the negative rho epsilon naught. Very often, where we are interested in finding the potential in a region where the charge distribution is zero. Okay, let's say conductor siya, kubaman ta basta conductor, the charge distribution rho is zero. Okay, there's no free charges residing at the surface or at the, let's say, surface area nga imuhang i-consider. So in this case, if if zero imong row, then the Laplace equation, equation 3 becomes the Poisson's equation becomes the Laplace equation given in equation 4. Or in Cartesian coordinates, we can have this equation 4 written in equation 5. We have del square v with respect to x square, del square v with respect to y square, del square v derivative with respect to z square. Okay, that's equated to 0. So this is our Laplace equation, and this is very useful. This is the Laplace equation. This is very useful and very fundamental because it appears not only in electrostatics but also in gravitation and magnetism. It also appeared in theory of heat and the study of soap bubbles. So ang iraha namang idea ani nganong magamit yun ang Laplace equation because of the idea of this is actually maximization minimization, maxima minima problem. Why? Because kuan naman ni siya, derivative ramang ka, di ba? Second derivative of any function with respect to x square, y square, or z square. And if you have the second derivative of something with respect to a second derivative of any function, then that's equated to 0, meaning wala siya local minima or minima, right? Kay di ba sa ato ang law of sa ato ang maxima minima nga problem is the first derivative x prime. So the first derivative would tell you the slope kung unsa ang imuhang unsay value sa curvature sa imuhang function. But the second derivative would tell you kung maximum ba siya or minimum, right? Meaning if the second derivative is positive, so kung positive siya, so ang imuhang function, right? Imong function is actually a minimum, right? Paana man na siya. Minimum siya. But if it's the other way around, if it's negative, so it's curved downward. So ang curvature niya, so it's maximum. So the second derivative will tell you if that function is if it's a maximum or a minimum. But for the Laplace equation, we will discuss it later. So yung second derivative is 0. Okay, let's consider the Laplace equation in one dimension. So suppose v depends only on one variable x, then the Laplace equation becomes this. And we know the general solution of this is kani mo na siya equation 6. Why? Because imo siyang ipabali bitaw. You take the derivative of this with respect to x, right? With respect to x, it becomes m. But if you further take the derivative of this with respect to x gihapon, so that would be x squared. So this becomes 0. That's why 0 na siya. So this is the general solution. So nanama idea dahil nga kani nga equation kuan man equation of a line. You are correct. That's equation of a line. So equation siya for a straight line. So it contains two constants a and b. Right? But in this case, we have constants m and v. These are actually fixed. So for instance, it might be specified na nga ang iyang potential niya is 4. Then at value at position x equals 1, and also na potential nga b equals 0 at position x equals 5. So easily makalculate naman nimo ang slope ana ug unsa ang y-intercept. Kay duha man nimong unknown, so duha po na imong equation. So we have 4 equals m, right, plus b. Then that ang isa kay we have We have 0 here. 0 equals 0 po ng m, so it becomes, oh, x equals 5, so we have 5m plus b. So imuha naman na siyang, you can actually solve this one giving you m equals -1 and b equals 5. So that would be your solution sa imuhang kaning duha ka equation. So if you have m equals -1 and b equals 5, so ang equation na dayon sa imuhang line becomes this. Okay? And ang iyang drawing is kana. Okay? So you can easily predict or determine the value of the potential anywhere along the line. Kani siya, along x, let's say x. So we can take a look at equation 6 and examine that there are actually two features behind it. We have equation 6. Okay. B equals mx plus b. So actually v of x is the average of, if you have, let's say, v of x plus a and v of x minus a. So ang iyang average niya is, of course, the v of x for any a. So we have this, v equals just take the sum of the two and then you divide by 2, you take the average. And then next is the Laplace equation tolerates no local maxima or minima, as I've said, because the second derivative of v with respect to, let's say, x, case one dimension naman ta, is 0. No? So since Laplace equation requires that the second derivative be 0, it seems reasonable that the solution should exhibit no extrema. Of course, wala siya extrema. Wala ga-exist nga extremum value. Maybe ang ihang extremum value may exist siya sa boundary or sa both ends. Now let's move on to Laplace equation in 2 dimensions. So in 2 dimensions, your Laplace equation becomes this equation 7. Okay. Again, wala siya local minima or maxima because of this equation. And this is a partial differential equation. And one cannot write down a general solution, at least not in a closed form. But nevertheless, it is possible to deduce certain properties common to all solutions. Let's say you picture out this scenario. Okay, you have x, y, you have area naman siya, so plane. Actually, if x and y, then the third dimension is v, the potential. So picture this thin rubber sheet overlay on a top of a cardboard box like a drum head as shown in the figure. Mo siya gi-cover og cellophane ba? Ano siya ang muhang surface kani siya. Okay? So the same food sa katong sa line nga ang v of x is actually the average, right? V of x plus a plus v of x minus a. Kanipod, of course, this is v of x kan sa tunga. V of x is actually the average food sa iyang vicinity, which is di naman line, so circle naman siya, right? So we have area na siya, so that would be, say, area sa imuhang circle. So that would be ang imuhang divisor diha, that would be the area. So, or the circumference, I mean. So kaning siya nga kuan have to be 2 pi r and then some potential dl, right? And this is circle. Ngayon na is line man to, no? Kani siya is like a circle na siya. Diba? You have 2 pi r. Or you have this. So the value of v at any point xy is the average of those around that point. Okay? Yang na ako'y point din so kana siya actually is the average of those area of this is the average of those around the point kana. So again, the potential v has no local maxima or minima. All extrema occur at the boundaries. Now for the Laplace equation in 3 dimension, Now in 3 dimension, the potential depends on x, y, and z. So the Laplace equation now becomes equation 8. Yeah. So the equation does not have a simple analytical solution as the 1D Laplace equation does. However, the properties of the solution of one-dimensional Laplace equation are also valid for solutions of the 3D Laplace equation. Let's look at two properties sa kaninga case. So the value of v at point x, y, and z, katong kayo na area man to, no? So the value of ang imuhang v ato is average siya at the point around it. Kanipod is the average, the potential v at a point x, y, z is equal to the average value of the v around this point. Since 3 dimension naman ka, so it's like kuha na siya ka ng surface sa sphere instead na circle siya. That's why you have this. This is the gisam ni mo tanan, right? Mo man siya katong sa line ka, isama naman mo v1 plus v2. Kani siya is continuous naman ka. You have a sphere. So this is the area sa sphere divided by katong area sa imuhang point around it, which is the area of the sphere. So we can prove the property of V. Consider the electrostatic potential generated by a point charge Q located on the z-axis, a distance r away from the center of a sphere of radius r. So let's take a look at this equation. Ako'y charge Q din hi. Tara. Ako'y charge Q din ha. And then I want to find the potential at this point P. Tara. So now ako'y distance D and then radius r, and then it has an angle of theta between the kanisang line and the z-axis. So the potential at P generated by charge Q is equal to, kana naman, di ba? Kani siya. So this is the equation of your potential. You have D, kanisang distance. But we can also express D in terms of R and big R in terms of small r and theta by using the law of cosine or the cosine rule. Tara. Then you substitute this expression of your D in half. Right? So becomes D equals square root of r squared plus small r squared plus big R squared minus 2r cosine theta. So the potential at P due to charge Q is therefore equal to Ra. And the average potential on the surface of the sphere can be obtained by integrating Vp, V sub P across the surface of the sphere. So the average potential is equal to, so you have your Vp here, substitute naman na siya diha. Then this is the formula, this is dA, right? And then this is your area, divide mo siya kay average man. Sum total divided by kaning area sa imong sphere. Substitute that one, you get this, and then you can actually look for the resulting integral of this, sa resulting integral niya sa table of integral. You can easily evaluate this one. Solve naman na siya. You get this, then you evaluate, you finally get this form. So this is a familiar equation, right? This is the potential potential at position R generated by charge Q. So the average potential on the surface of the sphere is given by this. So muna siya ang average potential niya, which is just the same as the potential due to Q at the center of the sphere. Exactly. Now applying the principle of superposition, it is easy to show that the average potential generated by a collection of point charges is equal to the net potential they produce at the center of the sphere. Okay, that's property 1. For property 2, The electrostatic potential V has no local maxima or minima. All extremes occur at the boundaries, as I said kanina, because of that kanisiyang del square V equals 0. Now, let's take a look at this. You find the general solution to Laplace equation in spherical coordinates. So, kani, I might give this as a problem set. I, I might mag-post ko siguro mga next week na. So, nakuha man na to ang general solution sa Laplace equation in Cartesian man to siya, right? Cartesian to siya. But how about Laplace equation solution in spherical and also cylindrical? That would be assign na siya. Now, let's discuss the uniqueness theorem. Magamit ni siya sa kaning special techniques. Okay. So we've seen that the electric field obeys Gauss' law, which in differential form is given by that. Right? Naka-familiar naman taan na. The field can also be written as the gradient of a potential function. So we get this one, right? And i-substitute mo din ha ang E or kani siya, ang E mo is del V, so mo siya i-substitute din ha. You get this, right? Now this equation is partial differential equation. This is the Poisson's equation. And its solution gives the potential for a charge distribution. Now in regions where there is no charge, rho is equal to 0, and it becomes a Laplace equation. Tada. Now let's look at the first uniqueness theorem. If you consider a volume within which the charge density is equal to 0, so na ako'y boundary, tapos na ako'y volume of any form na siya, basta kaya na siya volume, and suppose that the value of the electrostatic potential is specified at every point on the surface of this volume. So it states nga that in this case, the solution of Laplace equation is uniquely defined. So, unsa pasabot? Uniquely defined meaning, nakuha nga system, and then the value of the electrostatic potential is specified at every point. So, ang solution daw nimo sa Laplace equation is uniquely defined, meaning, kung ang sayong makuha nga solution, puro gina siya ang only solution. You can never find another equation nga kana ang ihang solution because it's uniquely defined siya. So it's like if you have boundary conditions, you have the following conditions nga na met, and then ang solution niya na is actually unique. Later on, magkata tayo example, mas masabta na siya. Next is the second uniqueness theorem. Related siya sa first uniqueness nga theorem. So it states that the electric field is uniquely defined if the total charge on each conductor is given and the charge distribution in the regions between the conductors is known. Let's take a look at this. So you have conductor 1, conductor 2, conductor, and so on. So if you have this conductor, tapos each conductor is given and the charge distribution in the regions between the conductor is known. Tara. In this case, that would be that the electric field or potential is uniquely defined sa kaning system dayan. Okay? So consider this example. So keeping those things in mind, katong mga uniqueness theorem and also the properties sa katong discuss ito ngayon sa Laplace, that will be useful in the following examples nga itong i-consider karon. So we'll be talking about the classic, actually it's a classic image problem. So consider this example. A point charge Q is held a distance d above an infinite conducting plane. So we have an infinite conducting plane here. The question now is, what is the potential in the region above the plane? Okay, so na ako'y charge Q din So na ako'y conducting plane. So based on nga idea, so possible, di ba nga, it is possible or maogi na mahitabo nga because of this charge, mo-attract na siya og mga charges po dinhi sa imong conducting plane. But since this is a conducting plane, the potential there is zero, right? Grounded man na siya diha. Okay. So our problem here is to solve the Poisson's equation in the region z greater than 0. Okay? So asa like dinhi ba or dinha ba siya sa iyang general equation if we want to find the potential at z greater than 0. So na siya single point charge Q located at 0,0D. Tara. And subject to the boundary condition that the potential is 0 at when z equals 0 since the conducting plane is grounded. Tara. And also V approaches 0, which if you consider a point far from the charge, so infinity ang imuhang kanisya. This is much larger than kung asa to na-locate ang imuhang point charge Q. So the electrostatic potential of this system must satisfy the following two boundary conditions, tara, such that ang potential nimo at the z equals 0, so this is z equals 0, right, is 0 imong potential because of the condition or given man siya nga ang imong conducting plane is grounded. Next is your potential approaches to 0 as your point in question kung asa ka mag-evaluate of potential approaches infinity. Infinity. So, of course, far na kaayo siya from the point charge or from the conducting plane, therefore the potential there is 0. So a direct calculation of the electric potential cannot be carried out because dili man given ang imuhang charge distribution, right? If given pa na, then we can just easily calculate it using this equation. Ano na rin ka? Rho d tau over r squared, r hat. Such is not the case here. Okay, so we need a different technique. So we'll be using the idea nga 0 na siya, tara, 0 po ni dinhi, kani nga condition. So magamit yung atong del square v equals 0, di ba? Being 0 diha Laplace equation, 0 ang imuhang rho or charge density. So the charge distribution on the surface of a grounded conductor does not need to be 0. So dili 0 ang imuhang sa conducting plane. Right? Sa katong conducting plane, not necessarily nga 0 na siya diha. It's just the potential is 0. So, really masud na ang classic nga image problem. Magamit ka og method. This is also known as the method of images. So, imo na usabon ang imong system. Instead na conducting plane, nawala to siya. So, muna siya ang nag-represent sa conducting plane, di ba, grounded. So, if you have a Q, magkuhan ka, kag na-reflection ba, mag-mirror. So, na-ay image. Ang Q, butang ka dara og negative Q na siya. Right? Paubos. Yep, negative Q. Of the same distance, the opposite na siya. So, i-recast nimo ang problem in such a way nga it would look like this. Method of images, na-create kag image. Okay? So this is a system wherein it consists of 2-point charges with charges plus Q and negative Q located at D and negative D along the z-axis respectively. So the electrostatic potential generated by these two charges can be calculated directly at any point. So at point xy0, meaning at the xy plane, the electrostatic potential is equal to, tara, right? Diretso naman na siya. Mura naman ang potential Q over R, where R is given by x square root of x square plus y square plus d square. Right? Muna siya ang sa taas, right? Kani siya ang sa ubos. And iyang potential niya is 0. So ato ni gamiton. Kay given man ni siya, nag-assume man tao, it's actually given kani sa problem. The potential is 0 at z equals 0. Ito na. Okay? Of course, if imo na i-add, 0 magid na, di ba? Okay, opposite sign, the same naman siya. So the potential of the system at infinity will approach to 0 with increasing r. Tama? So if i-approach mo infinity, that would be over infinity. This becomes 0. This becomes 0 as well. So satisfy na siya nga condition. At at x, y, and z approaches infinity, v approaches infinity. At v approaches 0. So at point x, y, z with z greater than 0, the electrostatic potential is equal to this. Tara. So general naman na siya. We have z minus d and the z plus d. If at z greater than 0. Okay? The same naman gyapon na if square na siya square, you can get later on ato na siya ikuan. Ang iyang absolute value ba tara. If you have. So we can solve for the induced surface charge density in this scenario by using this idea. Kani siya nga formula. This is given from the previous nga lecture. This is taken from the idea that the potential is discontinuous at the interface. Tara. Naman ta atong E above minus E below is equal to negative, is equal to positive sigma over epsilon naught. But we know, di ba nga, ang potential niya is continuous man, above o below. However, ang iyahang gradient sa imong V above o below is discontinuous. That's why we have this, kani, imong the change sa imong potential with respect to Z is it's discontinuous given by sigma over epsilon naught. So given this equation, kaning equation, you substitute the solution for V in this equation. Mo na siyang i-derive. You take the derivative of this with respect to Z, then you will get the sigma, which is the surface charge distribution. So we find this one. So kamo na lang bahala og kanani integrate sa inyong own convenient time. You should be able to check na mo na siya magawas. Kana. So this is the sigma. Mo na siya ang sigma nimo. The surface charge density. So the total charge on the conductor can be calculated by integrating the surface charge. Diba? Makuha naman nimo ang total charge given the surface charge expressed in this equation. Tara. So we have your sigma of r, and then the area is rd theta. And then of course r is integrated from 0 to infinity kay infinite conducting plane man to. Sorry. Hindi mo naman eh. Infinite conducting plane. Where r square equals x square plus y square. Mo na i-convert lang. So, kato imuhang equation na ganina sa imuhang v. Kasi ano man mo sigma, right? Mo siya i-substitute to. This one is r square. That's why na ako ani. Tara. We have r square plus d square to the 3 half. And then just evaluate the integral of that. Using the table of integral, you can get this. Then evaluate the resulting integral from 0 to infinity, you get this. And so the total charge, of course, is negative q, di ba? So muna siya ang induced charge, di mo? So you have positive q sa katong bana man to. You have positive q. So ang induced charge mo diha is negative q. So the force exerted on point charge q can be obtained immediately by calculating the force exerted on the point charge by the image charge. So the force is equal to F is Q1, F is ano naman na, di ba? F is Q1, Q2 over R squared K. So you have this. So the same naman to Q1, Q2 becomes positive. And then Q squared, so ang one distance between the two is 2D. Okay, if you have your Q here, naman to dali ang negative Q, then this is D, this is D. All in all, you have 2D. Excuse me. However, the total energy of the system is given by total energy is kung unsa to ang imuhang one half pa siya sa imuhang real image, right? One half siya sa image. So you have ang imuhang energy or imuhang work is just force times d naman na, di ba? So you have your force times d, diba? You get the work or the energy. So you have this. And then i-divide mo siya og one half because mo na siya ang kaning pagkuha nimo sa the total energy sa imuhang imong real system. It's actually half sa imuhang image. So that's all for now. Kay pwede kay mataas ang video. The next video na pod will discuss on the solution sa kaning problem.